This is my presentation on Quaternions and how I think it's going to develop a better unified field theory and set a foundation for a unified field theory. And my research is based off Douglas B. Sweetzer's Quaternions and Special Relativity. Okay, so we start off with the vector system developed by Heaviside and Gibbs, and well, Hamilton branched off of that vector system and decided to, and he actually founded the Quaternion system. So what is a Quaternion system? The Quaternion system is based off 3 vector units plus 1 scalar unit. Now we know we can't combine scalar units and vector units, but Quaternions allow us to do that. Quaternions are better suited for relativistic quantities, like we're using photons, or we're using, since a photon is the most relativistic, since it has no relativistic limit. Quaternions, which he goes on to later in depth, I will not be going on later in depth, are useful for developing quantum electrodynamic equations. Okay, so what are Quaternions? Quaternions are the generalization of the complex plane into 4 dimensions. Now, we know that the complex plane is a generalization of the real number plane into 4 dimensions additionally. So it takes the imaginary axis and the real number axis. Okay, now what Hamilton did was, or I'm going to say Hamilton wrong, well, he added these 2 axes. Now, how he added these 2 axes, it involves the Taylor series, and I hate the Taylor series, so we're not going to go into that. So when he added these 2 axes, which we're going to go into a little bit later right here, he said, okay, given the imaginary axis and the real number axis, let's plot a vector upon the complex plane. Let's plot this vector right here. Okay, and he asked himself, how are we going to get this vector to rotate 180 degrees? Well, we all know to get, or at least in the complex plane, to get a vector to rotate 180 degrees, we're actually going to multiply it by a negative number. So when we multiply by this negative number, we can come to the conclusion that multiplying it by a negative number gives it 180 degrees, right? Now, if we multiply, now he asked himself, how do we get a 90 degree rotation, right, on the complex plane? Okay, what we're going to do is we're going to say, okay, x times x, so what value of x gives us a 90 degree rotation? So we're going to say x times x equals 180 degrees, because we know 180 degrees gives us a negative rotation, which gives us a flip. So x squared equals -1 is what we ended up finding. But we know anything squared can't give us a negative number, which is what developed the imaginary axis. Now he did this to find the j-axis and the k-axis the same way, but he did it instead of generalizing the root of -1, he ended up generalizing commutability between the complex number plane and the Quaternion number plane. Now, that is how the complex number plane was derived, and that's how it was made. And like I said, he did that for the j-axis and the k-axis to the same thing, just with commutability. Okay, now, if we rotate a vector by an arbitrary angle, we calculate the root of -1, like I just finished saying. So what he found was that z forms a vector of length, so z forms a vector of length p, right here, making theta angle with the real number system. Now he found that any point on the complex plane can be written as z equals x plus I hat y. Now you can still follow the law of norms, and you can still find the length of p using the standard distance formula. Now the next question is, okay, we know how to get the imaginary plane into the real number plane. We know how to rotate it this way, but how are we going to rotate something that's on the imaginary plane into the Quaternionic planes, such as j hat and I hat, or j hat, I hat, j hat, and k hat? How are we going to do that? Well, we found that the way we're going to, I'm so thirsty.